Good morning, children. In today's class, we are going to discuss about certain types of ligands. In yesterday's class, if you remember, I had discussed with you about ligands and central metal ion. I had told you that ligands are those groups which are attached to the central metal ion by the help of coordination bond, okay, and that's why see ligands are called as donor atoms. Now in today's class we are going to discuss about some types of ligands. We have some common ligands, and these nature of these ligands are they are neutral in nature. See, the first ligand we have over here is the first ligand we have over here is see the first ligand we have over here is ammonia. So ammonia is represented by NH3 and its charge is 0. And while we have to name it, we name it as amine. If copper contains 4 ammonia, it is called tetramine copper. It is called tetramine copper. Okay. If copper has 4 ammonia attached to it, it is called as tetramine copper. It is called as tetramine copper.
হ্যালো।
Yes. বলুন। So it is called as tetramine copper. Now the next one we have is water. Now water, it is called H2O and its charge is also 0. It is called as aquo or aqua. Next is phosphine pH3 and its charge is also 0. It is called as phosphine, right? We have next one nitrogen oxide NO. Its charge is 0 and it is represented as nitrosyl. Then we have carbon monoxide. Its charge is also 0 and it is called as carbonyl. After that we have pyridine. Its charge is 0 and it is called as Py. Pyridine is represented as Py. Okay. Then we have triphenyl phosphate C6H5 whole thrice P. Its charge is also 0. It is represented as triphenyl phosphine. Okay. Next one, thiocarbonyl CS. Okay, and its charge is also 0. While naming it, we name it as thiocarbonyl. Next we have thiourea NH2CS NH2. Okay, so instead of C double bond O, we have C double bond S, so it is called as thiourea. Its charge is also 0. Now we have some examples of multi-dentate ligands. Multi-dentate ligands means these are ligands which can coordinate with a number of sites. The first one is oxalate ion. Oxalate, you can see the chart C double bond O, C double bond O. This is the oxalate one, right? Its charge is -2 and is abbreviated as OX, and it has 2 donor sites. 2 sites it has is its 2 donor sites. After that we have acetyl acetonate. See this structure, acetonate. If you want on the structure, please copy it. Its charge is also -1. It is represented as ACAC and its donor sites are 2. Can you see 2 of the arrows? These 2 arrows shows that its donor site is 2. Okay. I'm giving you 2 minutes time. If you want to copy, please copy it. Have you copied it? See, after that we have the next one, that is dimethyl glyoxyl ion. Dimethyl glyoxyl ion. What is the formula? It is represented as CH3C double bond NO, CH3C double bond NOH, and its charge is -1, and it is represented as DNG. And how many donor sites? It has two donor sites. Okay. Next one we have is glycinato. Glycinate, actually it is a glycine molecule which has two of the donor side. One point it is donating with the nitrogen, other point it is donating with the oxygen. And what is the charge? The charge is -1, and it is represented as GLY. Okay, and the donor site is 2. Next, we have ethylene diamine triacetate ion. Ethylene diamine triacetate ion. Here also it is represented as EDTA -3. And what is the charge? Charge is -3. Can you just see the 3 points where this minus charge are been showing? See the 3 points where this minus charge is been shown. Okay. And it is called EDTA -3. A number of donor site is 5. Next, we have ethylene diamine tetracetate ion. Here, the donor site is 4. Here, you can see that the donor site is 4. It is represented at EDTA -4, and the number of donor site over here is 6. So, that is how we have this type of multidentate ligands, and this is way how they connect with each other. Okay. So, if you want to copy it down, copy it. I'm giving you 2 minutes time, just copy it. Okay. After that, see, we are moving to the next part of the topic, that is coordination number. Now, what is called coordination number? See, coordination number of a metal ion in a complex may be defined as the total number of ligands or donor atoms to which the central metal ion is attached to it. So, if you want to write down the definition of coordination number, just write it down. Coordination number is the number that denotes the number of ligands by which the central metal ion is attached to it. Okay, so if you want to write down definition of coordination number, you just write it down. The coordination number in a complex is defined as the total number of ligand donor atoms to which the central metal ion is attached to it. To which central metal ion is attached to it. So just write coordination number of a metal ion in a complex is defined as the total number of ligand or donor atoms to which the metal ion is directly attached to it. To which the metal ion is directly attached to it. So coordination number of a metal ion is in a complex is defined as the total number of ligands, donor atoms to which the metal ion is directly attached to it, to which the metal atom is directly attached to it. That is called the coordination number. See, suppose I write one example, then these things will be just clear to you. Say, suppose I say, can you see the white page? Suppose I have central metal ion as cobalt, right? With that cobalt, I have been attaching with Cl are there. There are 4 Cl. So what is the coordination number? The coordination number of cobalt is 4. Why 4? Because it is attached with 4 chlorine atoms. As it is attached with 4 chlorine atoms, so its coordination number is 4. So actually what it denotes, coordination number tells you the number of ligands by which the central metal ion is attached. Okay. After that, we have the next one is coordination sphere and counter. The central metal atom or ion and the ligands directly attached to it are enclosed in a square bracket and is collectively termed as the coordination sphere. Now, what is that coordination sphere? Coordination sphere means the central metal atom of the ion and ligands are directly attached to it are enclosed in a square bracket and is collectively termed as the coordination sphere. The ionizable groups are written outside the bracket and are called as counter ions. For example, in the complex, see the ions which are present outside the third bracket is called the counter ions. Okay. After that, we have the oxidation number of the central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands were removed along with the electron pair. See, in this case, suppose I say that if all these 4 chlorines were being removed, then what would have been the charge? Cobalt charge would have been plus 2. The charge in cobalt is plus 2. But as there are 4 chlorine, the total charge over here comes to minus 2. Why minus 2? Because each of the chlorine is having minus 1. Cobalt is having plus 2. So minus 4 plus 2, the total charge is minus 2. So I can just have a sulfate over here because see, sulfate has a minus 2, but this minus 2 cannot be possible, so I have to put some positive charge. So it can be like this, K2, K2COCl6. Why it is called K2COCl6, Cl4? Why is it so? Because see, each of the cobalt has a charge of plus 2, the cobalt has a charge of plus 2, each of the chlorine has a charge of minus 1, so minus 4. What is the net charge? Net charge is minus 2, and each of the potassium has 1 plus, so they are plus 2. So ultimately the complex come to K2COCl, K2CO. So oxidation number of the central atom, if you want to write down the definition of oxidation number of the central metal ion, so just write it down, that oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed. All the ligands are removed along with the electron pair that are shared with the central atom. So coordination number of the central atom, you write the oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands were being removed. So in a complex, what we see that there is a central metal ion. Around the central metal ion, these are the ligands in this case are being attached to it. If somehow I just remove all these ligands, the charge that is left out, that is called the oxidation number of the central atom. Charge that is left out is called the oxidation number of the central atom. Charge that is left out is called oxidation number of the central atom. So I can say that cobalt is the central metal ion, with which these are the charges of the ligands. If I remove all these ligands, the charge that is left out is called the coordination number of the central metal ion. So here we can see cobalt is the central metal ion. It is attached with ligands, and in this case the ligands are Cl. How many ligands are there? There are 4 ligands. Each of the chlorine has a charge of -1. So ultimately what is the net charge coming? Net charge coming is -2. And so that is satisfied by potassium. Okay, that is one example. So have you understood what is oxidation number of the central atom? After that, we have the next one is homoleptic complex. What is the homoleptic complex? The complex in which the metal atom is bonded to only one kind of donor atom. Then that is called homoleptic complex. So here we are discussing about homoleptic complex. What is a homoleptic complex? Homoleptic complex is a complex in which the central metal atom is attached with same types of ligands. Here we can see that it is attached with same type of ligands. All these 4 are chlorine. So that is example of a homoleptic complex. But if it is attached with separate types of ligands, then that is called heteroleptic ligand. See here, another example will make you clear. See, I'm writing one. Suppose I have the same cobalt. It is attached with chlorine, ammonia, and ammonia. Okay. So here, can you just see we have the central metal and cobalt, right? Central metal and cobalt, it is attached with 2 different types of ligands. It is attached with 4 of the chlorine and 2 of the ammonia. So that is example of a heteroleptic complex. If a ligand has, if a complex has, or the central metal atom has same types of ligands attached to it, then that is called a homoleptic complex. But if it contains different types of ligands attached to it, it is called heteroleptic complex. It is called heteroleptic complex. And here it is called as homoleptic complex. Okay. Why is it called homoleptic complex? Because in the above one, the ligands attached were of the same type. So it is example of the homoleptic complex. But in this one, the ligands attached to the central metal ion is actually not the same type. So it is called a heteroleptic complex. So if they ask you the question, what is the basic difference between a homoleptic complex and a heteroleptic complex, I hope you can answer it. That is, homoleptic complexes are those complexes in which the attaching ligands are of the same type. If the attaching ligands are of different, example of a heteroleptic complex. That is the example of a heteroleptic complex. Is this part clear to you, children? Okay. After that, we will discuss the nomenclature, or before that nomenclature, we have the next one is called denticity and chelation. That is chelating ligands. Denticity or chelation. It is called denticity or that of chelation, or which are called as chelating ligands. Okay. Now we are going to discuss about the denticity and chelation, or that is called as chelating ligands. What are called as chelating ligands? When a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site. When a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site, then a ring-like structure is obtained. It is called as gillette ring, and ligand is known as gelating ligand. It is called as gillette ring, and ligand is called as gelating. And the ligand is called a gelating ligand. When a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site, When a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site, then a ring-like structure is obtained. It is called as a chelate ring, and the ligand is called as a ligand. So if you want to write down the definition, please write it down. When a ligand simultaneously coordinates to a metal ion by more than one donor site, when a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site, then that ring-like structure is obtained. It is called as a chelate ring, and the ligand is called as chelating ligand. It is called as chelate ring, and the ligand is called as a chelating ligand. The number of such ligating groups indicate the denticity of the ligand. That indicates the denticity of that of the ligand. Some common examples of chelation are shown as follows. Just see the example. In this example, can you see we have platinum that is attached with two chlorine over here, and we have ethylene diamine over here. This ethylene diamine forms ring-like structure. As it ring-like structures, we can say it is a bidentate chelate, or it is forming a bidentate chelation, right? On the other hand, just see the next one. We have platinum over here. We have ethylene diamine over here. Another diamine over here. So how many of them are coordinating? It is coordinating with a tridentate chelation. Why? Because this is number one, number two, and this is the third one. So how many are joining? There, it is joining by three. So it is called as a tridentate chelation. It is called as tridentate chelation. Here it is called as bidentate chelation. Why it is called bidentate? It is called bidentate chelation because in this case it is forming two chelates have been formed. One is this ring, other is this two Cl is attached. In this case, there are two rings and one is attached. Okay. See the next example. The next example will make you clear to you. See this example. In this case, what we see that platinum is in the center. It is connected with three of the ethylene diamine group. So how many chelate it is forming? It is forming a tetradentate chelation. Why? Because there chelation in the previous two there was 3 points and 2 points of chelation. So one is bidentate, other is tridentate, and next one is tetradentate chelate. If you want to copy it down, please copy it. Then I would move to the next part of the chapter. I hope you have copied it. See, after that, we will discuss about the coordination sphere. We will discuss about the coordination sphere, or what by coordination sphere. See, in the coordination compound, the central metal atom or central metal ion, along with the non-ionizable ligands attached to it, is always enclosed in a square bracket and collectively termed as the coordination sphere. So what I am wanting to tell you that in the coordination compound, the central metal ion along with the non-ionizable ligands attached to it is always enclosed in a square bracket. We enclose it in by the help of a square bracket and is collectively termed as coordination sphere. The portion present outside the square bracket is called ionization sphere. The portion present outside the square bracket is called ionization sphere. For example, in a complex CuNH3 whole 4 sulfate. See, in this complex CuNH3 whole 4 sulfate, the part Cu NH3 whole 4 plus 2. See, we are enclosing them in the form of a type of bracket, and that is called as the coordination sphere, and the sulfate radical constitutes the ionization sphere. Sulfate radical constitute the ionization sphere. It may be noted that the species present in a coordination sphere are non-ionizable. That is, the species present in a coordination sphere are non-ionizable, and the species present in ionization sphere are ionizable, and the species present in the ionization sphere are ionizable. There are two things: one is non-ionizable, other is ionizable. Okay, if you want to copy it down, just copy it. See, here in the adjoining diagram, can you see that is, here we have the tetrahedral entity, right? And we have the square planar entity. That is, the coordination sphere is represented by this. I'm giving you 2 minutes time, just copy it, then I would move to the next part of the chapter. Okay. I hope we have copied it. See, after that, the next part of the chapter is coordination number or coordination ligancy. Okay, coordination number, or that is simply called coordination ligancy. Okay, now what is called coordination number? It is the number of ligand donor atoms which are directly bonded to the central metal atom. Just write it down. It is the number of ligand donor atoms which are directly bonded to the central metal atom in the coordination sphere. It is the number of ligand donor atoms which are directly bonded to the central atom in the coordination sphere. See, as you could see over here, that in the complex K2PtCl6, 6 chloride ions are present in the coordination sphere, and therefore the coordination number of platinum is 6. Why? Because I could see that there are 6 platinum, so the coordination sphere it is 6. Okay. Similarly, in the complex Ni NH3 whole 4 Cl2, the coordination